Hey guys, so we already kind of hit a few things in these demos, but I'm gonna kind of walk through it, make sure that we get through everything else that we need to talk about. So first thing on here is gonna be surface tension. I'm gonna post this video. It's pretty cool. We're kind of linking these things back to aquatic science little by little. So the first thing we're gonna do here is if you watch this video about surface tension, I thought it was kind of interesting. You don't have to watch it, I guess, but there's a water strider on there, and it just shows how things that can kind of live on the surface of water that really shouldn't. And this dude actually hunts other organisms on top of the water, so it's kind of cool to watch. But anyway, we said surface tension was those cohesive forces in water that basically allow it to resist spreading out. It's basically the property that these little dudes use to kind of skate along the surface of water. Then we talked also about, kind of in the same vein, we talked about capillarity, which basically just says that cohesive and adhesive forces give water the ability to crawl up through narrow spaces. In this particular, this is kind of like the demo that we did, except this uses sand, clay, and loam, which clay is finer even than sand, and then loam is a mixture of sand and clay. Where that kind of applies to the real world, obviously lake bottoms will hold on to water, and it can't really move through it very well. Typically our lakes have clay bottoms, which allow the water to stay there longer, and also will allow it can draw water up through the clay because it can use that capillary action to get up through. So anyway, if you've ever heard of water wicking through something, wicking is basically capillary action. If you put a string in water, water can crawl up that string through those cohesive and adhesive forces. Then the next thing that we're going to have to spend a little bit of time on is water being the universal solvent. How does water dissolve stuff? It all comes down to polarity still, so we're not going to get into that too much, but I'm going to show you a video here in a minute that kind of tells us how certain things dissolve. But the reason it's important is because we have pollution. And anytime we have a pollutant that can dissolve in water, that makes it a little bit more difficult to remove from the environment. Then freezing point depression, boiling point elevation, we'll talk a little bit about that later. It's not as big of a deal right now. And then pH, certain things that can dissolve in water and then affect the pH of water becomes pretty important. And then solution densities. We talked a little bit about density based on temperature. And we'll actually link that to something a little bit later, probably next week. But we can also, when we dissolve salt, for instance, in water, that also increases its density. So we can have density layers based on salt water and fresh water, which you'll see something on that in just a minute. So let's start with this making a solution thing. This guy does a pretty good job of talking about ionic and covalent compounds. And kind of how they dissolve differently. I always call this a dead polar bear gang fight. So they're basically initiating these molecules into their gang. And the way that it does it is the water molecules are going to surround the particles. So pay close attention to how ionic compounds dissolve, because they actually separate into positives and negatives, and then the ears will surround them, and the mouth will surround, the ears surround the negative ion, and then the mouth surrounds the positive ion. So pay attention to that when you get there. I'm actually going to just kind of run through this real quick so you can see it. He's not talking now, so you'll want to watch it, but I'm going to show you the keys to kind of pay attention to. So he talks, and then he gets to where they break apart in water. Notice that when these guys, get that out of the way, when these guys break apart in water, these are the ionic compounds, they dissociate into their ions. So this is Cl minus Na plus. And then sugar actually, if I go a little bit further, it actually dissociates into its molecules. So what I usually do is I come in here and I have the kids draw in kind of what's going on. So if we notice from this drawing, this is the ionic compounds. This is Na, which is positive, and then Cl, which is minus. So this is a plus, this is a minus, this is a plus, this is a minus, plus, minus, so on. So I call it the polar bear gang initiation, because basically what happens is the water molecules come in and they align themselves around these so that the ears, remember the mouth is negative, the ears are positive, so around the sodium ions, the ears will all be facing away, right? And so that's really important because this side is positive, this side is negative, so they align themselves negative to positive, much like our cohesion stuff was. So same thing's going on here. Now around one of these negative guys right here, they will orient themselves where the ears face toward. So it'll look something like this. So I would encourage you to either commit that to memory or jot that down, because that will probably be a quiz question. It'll be something to the effect of, you know, if you have a water molecule that looks like this, or I'm sorry, a particle that's surrounded by molecules that looks like this, if we notice all of the ears are facing away, right? So those are all the positive sides, then that means that this must be a positive particle because the negative mouths of those water molecules are facing them. So basically the question might go somewhere along the lines of what is the charge of the particle that is being dissolved in this scenario. Now, the sugar is a little bit different. Basically, the way sugar molecules work is they are polar as well. So somewhere in this molecule, usually around these oxygens, there becomes like a negatively charged side, which means that there's a positively charged side somewhere else. And basically, it takes several water molecules to kind of work together to force these guys apart. We won't talk too much about what exactly that looks like. But basically they work together to pull them off the crystal lattice structure of the covalent compound. So for water to dissolve covalent compounds, though, they have to be polar covalent like water is itself. So back to the video, I would give this a watch. It's kind of shows how things are dissolved, but then I would also add this to like a drawing or a notebook or something that you might be using, so that you can see what's going on. So yeah. Hey guys, as I was kind of putting that solution video together, I realized that it's probably enough information if you watch these two videos that were embedded in the slideshow separately and then add this to it. It's probably enough information for today. So I'm going to go ahead and kill it here, and then we'll pick up next time on the factors that affect solubility, and then what things do dissolve in water, and how some things are beneficial and harmful, and then what that means to aquatic environments. So we're going to end it there, and we'll pick up with it next time.